Now that we know how to calculate the sample standard deviation, or work with the sample standard deviation and the sample mean, we can walk through the process of calculating a confidence interval for a mean. Now this process is very, very similar to the approach that we use for proportions. The only differences are how we're estimating the standard error, so we have a different formula, and which model we get our critical values from. So again, we're going to use the t distribution when we're working with means as described on the previous page. So let's start with a single example of a sample of 9 men with a mean height of 72 inches and a standard deviation of 6 inches. And these are slightly artificial numbers made to make the calculations a little bit easier for us, but this isn't that far off from reality. So we want to calculate a 95% confidence interval for the mean height of all men. Assuming these men are a good representative sample of all men, we want to calculate a 95% confidence interval. So the first thing we're going to want is our standard error. The formula for the standard error of a sample distribution of means is the standard deviation divided by the square root of n. Here we're going to use the sample standard deviation because that's the only thing we have. So we take our sample standard deviation divided by the square root of our n, so 6 divided by square root of 9 is 3, gives us 2. The next thing we're going to need in order to plug into our calculator is the degrees of freedom. So remember, the degrees of freedom are just 1 less than the sample size. N minus 1, so in this case 9 minus 1, means we have 8 degrees of freedom for this process. So now what we want to do is calculate the t critical value. So just like when we were working with the normal distribution, we want to find the cutoff at which we catch that middle 95% of the data. You can look these up in a table, but again, the values in StatCrunch tend to be a little bit more precise. So if we go to StatCrunch, click Stat, Calculators, now you're going to start to notice that in addition to the normal here, we have a lot of other distributions. We're only going to look at a handful of these, but if you're ever interested to go through and play with some, please feel free. Here we're going to look at the t distribution. And you'll notice that the primary difference between this and the normal calculator we had before is that this has a box for the degrees of freedom rather than a box to set the mean and the standard deviation. So every time we use the t distribution, we're going to be using the standard t distribution with a mean of 0. Now, the standard deviation is a little bit trickier, and we're not going to worry about that, but all we need to worry about is this degrees of freedom box. So now we're going to enter 8 degrees of freedom, because that's the value we calculated on the other screen. Now we want to find the cutoff for the outside 2.5% in each tail. So we want the middle 95%. So there's 5% left in the tails combined. Divided by 2 is 2.5% in each tail. So we put in 0.975 to get the upper cutoff. I like that because it gives us a positive value. You're going to notice a few things here. First is that this value is substantially bigger than when we had the normal calculator. So I'm going to go ahead and pull up a normal calculator, Stat, Calculators, Normal. Just move it over here. I'm going to do the same value here, 0.975. We get that 0.196 that we saw before. The value, the difference here is entirely driven by how thick these tails are. Now, if I make this value very, very big and compute it, we get down, excuse me, it doesn't hold my value for me, we get down to very nearly our value for the normal. That change is just about these tails becoming thicker or thinner based on these degrees of freedom. So if we go back to our 8 degrees of freedom, plug in our values, this 2.306 is the value we're going to want to use for our calculations. If you were doing this on a calculator on your computer, I would use Control-Copy right now, open up a calculator, and plug these in directly. Instead, we're going to walk back through the calculation here, and we're going to see that we get 2.306. Just a reminder that we got that value from StatCrunch. So because the t, like the normal, is symmetrical, we only need one side of the distribution. We could just as easily put in 0.025 for the bottom 2.5%. We just get the negative of the same value. So now we want to calculate our margin of error. Remember, this is how far we have to reach to think that we're reaching back to the true population mean. So in the case of proportions, we had our z star times our standard error. Here we just have t star times our standard error. So 2.306 with the additional values gives us a margin of error of 4.612. Our confidence interval is just our mean plus or minus that margin of error. So again, our mean from the sample plus or minus the distance we think we have to reach to get back to the true population parameter most of the time. So 72 plus or minus 4.612 means that we are 95% confident that the true mean height of all men lies between 67.39 and 76.61 inches. This is how we go through the process of calculating a confidence interval for the for a population mean.